finite volume method for convection diffusion. So for the upwind finite volume method, for the convection diffusion, we have the central finite volume method. A is diagonally dominant. That is because, and we shall now do the analysis to simplify it for SP equal to 0. The source term is always a discussion on its own. The coefficient that we have in the western, on the western side, that is in the system, it is minus AW, capital W. That will appear in the lower subdiagonal, and the modulus of that is simply AW, and that is, since it is positive, then we have already argued for that before. That was the AW itself. We have here many AWs, but the point is that this is the diffusion conductance plus the FW plus, and then we have already argued for that to be larger or equal than 0. Similar, the diagonal that is coming from the eastern coefficient A east, that is the upper subdiagonal, the modulus of that is AE, and that is AE itself because it is positive, and that was DE. Let's see, and that was, I think, minus FE minus. And then we had already also argued for that is also greater or equal than 0. In any case. And the sum of them, the sum will also then AW and AE, they will also be larger or equal than 0. But now the point that we want to make is that the center coefficient, that is equal, that we had derived before, it is equal to the western plus the eastern coefficients. And that is equal to the individual coefficients, that is the modulus of AW plus the modulus of AP. Because both of them are positive, so we can remove the absolute values, and then we can also put them in again, that doesn't matter. And then we have here, that is equal to the modulus of minus AW plus the modulus of minus AE. So then we have that the center coefficient is equal to the sum of the modulus of the neighbor coefficients. And so that is, so this part here is important, and that we have the equal. So, but then we need that this has to be, the center coefficient has to be larger than the sum of the neighbor coefficients for at least one node P, or one cell P. And if we have a situation that the neighbor coefficient, that we have the AE, if that is, let's see, how can we write it? We can write it in this form. If we write, if we have this and minus AE, if that is smaller than AP for at least one P, then by this equality we have this satisfied always, but we have this in addition for 1p, then the matrix is diagonally dominant. So, and from where do we get this condition that we need? Remember, we had the Dirichlet boundary condition on the left. And in the Dirichlet boundary condition, we had the AW not involved in the system, but it was involved in the AP. So in our case, we get it from the left boundary. So we get this condition here from left, from Dirichlet boundary condition at left boundary. And that's the same as we had in exercise 8. Because the AW will not appear in the system. We have that put on the right-hand side with the boundary condition, but it will appear in the center coefficient. So then we have the center coefficient is the sum of AE and AW, and then this is done away. And then we have this. And in our case, both the AW and the AE are larger than 0. So then we have it. So that's the argument that we need. And then, if we have diagonal dominance, then we can solve the system by the TDMA. So the linear system that we get, A phi equal to SU, can be solved by Thomas algorithm which is also called TDMA. So then we have no restriction here on the self-packing number. So then that is also the advantage of the method. So the upwind finite volume method for the convective flux, we use always the central finite volume method for the diffusive flux that is not restricted by the condition that we had for the central method, which was small equal than 2. So here you can use larger than 2. That's, there's no restriction to it regarding diagonal dominance. However, the disadvantage with this method, if you apply it and you compare it with the central method, when the self-packing number is smaller than 2, that the results are worse. Because the method for the convection is only of order delta x. It is still of order delta x square for the diffusive part. But you get numerical diffusion by that. So that is, on that we get numerical diffusion. Therefore, regarding accuracy, the central method is better. But this is more general, this is, we say, more robust. So you can use it, but you should be very careful with it. And in practical applications, usually one uses it only if nothing else works. Because you should rather use a higher order method for the convection. Let us look at a higher order method that you can use. That is a method that has the acronym QUICK. that stands for quadratic upstream interpolation for convective kinetics. And that is due to Bernhard of 1979. So if you invent a new method, you should also invent a good acronym. So we have already seen this, in fact, when we discussed the muscle approach. I didn't show it here, but it is in the lecture notes. So there you can look it up. That is in the lecture notes. And that is in 6.4 to 6.7 and table 6.1. And that is on pages 58 to 59. And it is under the big heading higher order methods. And you can actually regard it as a special form of the muscle without limiting. So it is more accurate than usual other methods, but it has no limiting. So it is not good for discontinuities. But if you have a smooth problem, smooth flow, or smooth heat transfer problem, then it is a good method. So let us look at the principle. We look at x and phi, and we assume that the velocity that we have here, that the velocity, let's see, one error might be enough here, that the velocity is greater than 0. So we have flow from left to right. Then we look at a cell with its neighbors. Let's see, we need some neighbors. So let's see if this would be the center, the cell P corresponding to J, that would correspond to the cell E, J plus 1. Here we have the capital W corresponding to the J minus 1. And we need now two cells more. We need one on the left side. I call it WW. That is J minus 2. And one on the right. Call it EE, corresponding to J plus 2. So that is already something new, because so far we had only finite volume methods that needed P and east and west neighbors. That's it. Now we need more. What we need to compute is the fluxes at the eastern and western faces. So that is then, say that it is our western face, that is our eastern face. And what we need there is now not only the value that we have at the cell P, or at the node P. If we look now at our nodes, say we have a value here, and we have a value, say at W, say we have it here, and say we have it in WW, let's assume we have it here, and we assume that we have some value at E. Let's see, that is here. If we have only flow from left to right, it's only these that we need. If we have flow from right to left, we need also some value here. But for this, we need only that. So what is the idea? The idea is to compute the western flux by doing an interpolation of the values at P, W, and WW. So that means we get a quadratic, quadratic polynomial that would look like something like this. So that is an interpolation of our values at WW, W, and P. And that will give us a value at the face. So that will give us then a value here. And this value here, that value that we get from the interpolation, that is then the value that we will use. That is then the phase value at the phase W. Likewise, we do an interpolation. Also, first thing is that you see the way we did it is we chose the node value and the upwind, the two upwind values to do that, to get it. So for P we chose the two upwind values because flow is coming from the left, this and this. To get the value at the eastern phase, we use then the value at E and the two upwind neighbors, which are P and W. So then we do a polynomial, say now, let's see, I'm trying to do that, I try to do an interpolation here. So that is supposed to be a quadratic interpolation of W, P, and E, this dashed line, and that will give a value at the boundary. Let's see. So it will get a value here, and that will be then our value that we take at the eastern phase. So that is the way the method works. So it does an upwind, as it says, quadratic upstream interpolation. It looks in the upstream direction, and there it takes then two upwind values to the phase. For example, here, the P and E are upstream to E, and it takes then one downstream. Then we have 3 points, and we can do a quadratic interpolation with them. So then we write down what we have been doing. So we do a quadratic interpolation of upwind values. That is phi W, phi W, and phi P to get the phi little w. So these are capital W's, these ones here, and this is a lowercase w because that's a phase value. And we use the upwind values phi W and phi P and the value at phi E to get the value at the eastern phase. If the flow is coming from the other direction, from right to left, U is negative, it is just similar. Then we would use to get this, we would use then the value in P and the two upwind values, which will be E and W. Here we will use the value at W, P, and E to get the value here. So what does that lead to? From that we get then the following formula, that is for we get 24a. That is the phi W, the one that we get then from this interpolation. If we do it with just a little calculation, we get the phi, the minus 1/8 is the weight on that, 3/4 is the weight on W, and 3/8 3/8 is the weight on P. And this and the next one, they are both for the UW greater than 0. So now the phi E, that is then gets the following weights. We have just to shift it now to the right, 1/8 phi W plus 3/4 phi P plus 3/8 phi E. Check that. Yeah, should be okay. And similarly, then we can do it for the left. So that would be then the situation when, that is the situation when U is positive. When U is, and that is, let's see, this is, let me see, I shall have to be a little careful here. Let me correct myself. This is for the UW greater than 0, and this is for the E greater than 0. Right? So then we have this. And similar then for the case when U is negative, we would get, I call it 24C, that is the phi little w is equal to, then the weights are 3/8 phi capital W plus 3/4 the weight on P minus 1/8 the weight on P. And here we assume that UW is smaller than 0. 24D, there we assume that the UE is smaller than 0. And then we get the phi E equal to, then we shift just the indices, phi P plus 3/4 phi E minus 1/8 phi E. So then we have everything here. So that method is second order. By instruction, it's even third order if we do it in that way. But in the end, when we use it in 2D and 3D, it comes into using the midpoint rule, and that is only second order. So that means that we have here the advantage of a higher order method. So I call it here second order accurate. So the approximation, to be precise, what we have done, since it is done with second order polynomials, then it is correct to second order. That means the error of phi E and phi W is actually third order. And so that is even order delta x to the power 3. But as I said, if you apply it in multi-dimensions, then you would use the midpoint rule. That you take an average and multiply it with the face area, whatever you have there. And 2D and 3D is only second order. And that would then give a second order only in the end. But still it's good. The disadvantage, however, the diagonal dominance is lost. It can be shown. So that is something that shares with the central finite volume method for convection. It turns out that the Self-Peckley number if that is larger than 8 divided by 3, 8/3, then that is lost, which is a disadvantage. And the other disadvantage is that we get now, in the general case, we get a pentadiagonal matrix, not a tridiagonal matrix. Because we have now in any case, either the west-west or the east-east involved. So we get a pentadiagonal linear system. And the consequence of that is that the solution needs about 4 times more operations, more floating point operations than the TDMA. So it's 4 times as costly. And the system that we have to solve, then we can write that in the form that we, instead of writing the matrix, calling it A, we call it P. P phi is equal to the uniform part of the source plane. So that is what we get. If we don't like that, but rather like to use the TDMA, but then we would have to use it several times, we could use something that is called deferred correction, that we shall see now. So the way out, unless we want to solve it, is possible, as we say here, you can invest this, but if you don't want to do it, you can use something that is called deferred correction. That is a more general method that you can always use when you have, say, a lower order method and a higher order method. The lower order method is usually more easy to solve. You use that, but then in the end, when you are finished with the iteration, you should then solve the higher order method. You should have solved that. So in that case, we can do it the following way. You use A that we have derived before from the upwind finite volume method for the convective fluxes and the central finite volume method for the diffusive fluxes to solve now the tridiagonal system of the following kind. That is the trick. We solve now this matrix that we also had before, the A, but now the price is we have to do an iteration. We have to do iterations. And on the right-hand side, we have the difference between these matrices. This is a tridiagonal matrix from the upwind method. This is the pentadiagonal matrix from the quick method. And then we do that times the value of the our unknown at iteration, at the old iteration, plus the SU. So the prices we have to iterate. The advantage, we can use the TDMA to solve it, because the right-hand side we can just compute from the old iteration, and then we solve this. So when we have convergence, so when the iteration that we have defined by this deferred correction is converged, that means that we have the phi at the new iteration is equal to the phi at the old iteration. So that is when we have convergence. Then we see when that is the case, the A phi and the A phi cancel, and we are left here with 0 minus P phi plus SU. But this is just the following. I write it. We get A phi is equal to A minus P phi plus SU, which is equivalent to, we subtract the A phi and bring the P phi on the left-hand side. That is equivalent to P phi equal to SU. So in convergence, we actually solve the problem that we want to solve, that is 25 for quick. So then we have here a higher order method. So then let's look at alternatives. We have already discussed some alternatives before, actually, when we discussed methods for solving scalar conservation laws and nonlinear. That were the TDD methods, total variation elimination methods. So that is look at what we discussed in chapter 6, part 1, and that is in lection, that is in the lecture notes. And you find it also in the textbook. In textbook it is 4.412, that section in Fletcher, Tannehill Anderson, I just tried et al., our textbook, and then there is a textbook that is actually useful for this part of the course, that is Verstegmaler Sekera. I cited it in the course overview of what we're discussing now. So there you can also look it up, and that is in that book, it is 5.10. I write it here, Versteg and Sekera. That is of 2007, it's second edition. So then you can use some TBD method. The preferred choice is to use the upwind method with muscle. So then you get higher order. And to use some limiter. There you have also some choices, but the most common one is the min-mod limiter that we discussed. We had also exercise 4, I think, on that min-mod. However, again, you get a pentadiagonal matrix, and then you can use the same trick as we used here for the quick. You can use deferred correction, or you take it into account and solve this pentadiagonal matrix. Okay, other options that you could use are also what we discussed when we discussed muscle. I just mentioned there are methods called ENO, essentially non-oscillatory methods, and weighted, essentially non-oscillatory methods. They usually involve even more neighbors, so you get even larger matrices, but you could use the same trick here. Either solve it, take this more work into account, or use deferred correction and using TDMA. So that gives you then an overview on solving the one-dimensional convection-diffusion equation for the steady state, for the steady convection-diffusion equation in 1D. Now we want to look at 2D. So then we use the finite volume method for 2D steady convection diffusion. Steady convection diffusion. So, what we have is the following. We have a grid, and let's see, we do it like here. Let's see, and, 3. Well, we need a little more here. So now we have a center node P. Neighboring nodes are E and W as in 1D, but now we have also the northern and the southern nodes. And what we need to compute are the fluxes. Now we have not only the eastern flux, let's see, we have not only the eastern flux and the western flux, but also the northern flux and the southern flux are to be computed. So that means we have now also to approximate those. So we have now, in addition to UW and UE, that are the velocities at the eastern and western faces, the western and eastern faces. So, thus we introduce now a little different notation as we had before. The difference is that in the notation now we include the area in our convective mass flux and also in the diffusive conductance. So we have then rho U W AW, and we have then the FE is also rho UE AE. So we assume that they are known and also these. But in addition we assume that also, so we assume that the velocities at the northern face, which is now the V, U is in X direction, V is in the Y direction. So it means we assume now that also the VS and the V north, and thus also the convective mass fluxes Fs equal to rho U Vs times the area at the southern face AS. So that and the convective mass flux at the northern face, which is rho Vn AN, that they are given. So that is now the assumption. And you see now the difference, I said it before, I say it again. Now the area is included in the definition of F. And likewise it is included in the definition of D, diffusion conductance. So then the 2D convection diffusion equation is discretized by the finite volume method as follows. The 2D, that is the steady 2D steady convection diffusion equation is discretized by the finite volume method and following. That is 27. Let's see. Take that over here. We have now to compute the fluxes over the eastern phase, that is as we had before, minus over the western phase, that is also as we had before. So these are all lowercase letters. But now we have also the convective fluxes to compute over the northern and the southern phases. There is the Fn, phi n, minus the F south, phi south. Again, all lowercase letters. And then that is equal to, on the right-hand side, we have the diffusive fluxes. That is as we had for the diffusion equation. But now, with these symbols, and again, I mentioned again, now the D contains the area. So it's the diffusion coefficient divided by the distance between P and E times the area at the eastern phase, times the unknown in E minus the unknown in P. That is the diffusive flux over the eastern phase. Then we have the diffusive flux over the western phase. In a similar way, phi P minus phi W. And we have the diffusive fluxes over the northern phase, which is then phi N minus phi P. And the diffusive flux over the southern phase, which is the diffusion conductance ds, phi P minus phi S. And we have the source term, which we treat in a similar way as before, as a uniform part, SU, a part that is dependent on our coefficient that we consider. In that case, it's for the point P, and that is multiplying the unknown at P. So the linear part, the coefficient of the linear part, that is the SP. So that is now what we do. We have already done the discretization for the diffusive flux using the central finite volume method. We have already done the linear approximation of the source term. So now we simply choose which method we use for the convection, to compute the convective fluxes. And there we can choose one of the methods that we just discussed. So that is up to us. But the ones that we mostly consider are the central finite volume method and the upwind finite volume method. So that means the phi n and the phi s that are the ones that we have here, these and these. They are approximated similarly as we discussed before. So they are approximated similarly as we discussed before for phi E and phi W. And if we use a central, so with central, or if we use upwind finite volume method for the convective fluxes, we get a penta-diagonal linear system. That is similar to the one that we discussed for the 2D diffusion equation, steady diffusion equation. And that can be solved by some iterative method which can be solved by some iterative method that we discussed before. And that was discussed in chapter 12. The thing that I forgot to mention when we discussed chapter 12 is simply that you have actually libraries that are available, public domain libraries, which have very good properties, especially when it comes to parallelization, because they are already using the message passing interface for parallelization, and you have them in C, C++, Fortran, Python, at PETSI. That's the PETSI library, which stands for Portable Extensible Toolkit for Scientific Computation. That is the one that some of my PhD students use. And you have also something that is called LAPAC, that stands for Linear Algebra Package. These are Fortran 90 subroutines for solving, for example, linear systems. Okay, so in the end, we solve this, and then it comes down to a similar problem as we discussed for solving the 2D steady diffusion equation. The warning that I give you, and you might think about that yourself, that is in 2D, if you have a problem where the flow is not following the grid lines, not this, not this, but if you have the flow, if the velocity u is like that, and you have here, for example, you have T cold, and you have on this side you have T hot, then you get something, you get very diffusive results just for the convection equation, just for the convection equation. So pure convection in that case leads to something that is called false diffusion. Or you could also call it numerical diffusion, but it goes under this name, false diffusion. You get very smeared results by using the upwind method. So for the upwind method, this is really a bad case. So just be aware of that. Okay, so we stop here.